Hello. Hi,
Morning.
Jose.
Oh, sorry, I can't see everyone here.
Hello, Klaus.
Hello. Nice to see you.
Hi, Gilad.
Good to see you.
Hi,
Very
Hagen.
well, all.
Good to see.
Hello, hello.
Yeah, so we're recording now both on YouTube and on the cloud.
Very good. Jose, you're still in California?
Yes.
Looks like the same room, yeah.
Yeah.
He's been sitting there for 2 weeks waiting for the next talk.
That's right. That's what we do. Yeah.
And Klaus, you're joining from home? And so, Rob, how many of the people at the NIH are back in the lab now?
Well, not that, I mean, I guess people doing experiments are coming in to do their experiments and then kind of, doing as much as possible from home still. But I am, yeah, I mean, Phil and Ad have been here pretty much the whole pandemic. Yeah, and I guess we should be starting to come back soon, but we haven't had any official word that, we're sort of supposed to be more on campus. I mean, everybody's been vaccinated by now, I would think, but so I don't know. I expect that, in maybe June or something, there'll be all back, but I don't know. That's my own opinion. I have no idea what the official word will be.
And so you're in the lab just occasionally now?
Yeah, I've been kind of in like a few days a week. Yeah. See some fossilized stuff on the whiteboard from like a year and a half ago or something.
Discoveries of old insights. Hi, Sophie.
Hello.
Hi, Stephen. Yeah, so we'll just wait a little bit until after the hour, until the numbers stabilize, and then get going.
Oh, I see. I managed to wear the correct outfit to match my picture.
Yeah, so you can tell it's authentic.
So it wasn't planned?
Well, I don't have so many outfits, so it's easy. Chances are not that low.
We were expecting a suit and a tie.
Oh, sorry.
Hagen, you didn't send him our dress code?
I forgot that. I'm sorry, Robert. Yeah, but typically it's either suit and tie or tuxedo.
We can wait a little. You can go and change, actually.
Still have 2-3 minutes. That should do.
See what I can dig out.
Hi, Vitor.
Yeah.
Right, Steve.
So Vitor, we solved the time zones, sort of. Not still, we have some.
Perfect.
Yeah.
Yes, now when I send this
so
to my
complicated.
students, I don't have to explain the right time for them.
I know it's very confusing with these time zones. It really is.
Either n+1 or -1, but you never know which sign.
Yeah. And then there's daylight savings in different places in different directions, and it really is confusing.
To remember whether it's UDT or UST or UVV or I don't know.
That's
Yeah, but-
why there is the standard ones that no matter where you are, you just look at UTC and that's it.
Right.
Yeah, but then there are places like Arizona that don't change the time zone. They don't. So it's
Yeah, that's a wise
Yeah,
decision.
but we even got the UTC wrong. So thanks for pointing it out.
No, it's the UTC that got it wrong.
Yeah.
Okay.
So numbers are still increasing. Let's wait another minute or so.
Where you see whether Twitter enthusiasm translates to actual enthusiasm.
Yeah, it's Twitter before the talk, and then there's Twitter after the talk. Okay, so it's 2 past the hour, so my Swiss heart is telling me we need to start. So let me welcome all of you. It's great to see so many of you again for our webinar on protein folding and dynamics. And it is a great pleasure to welcome Robert Best for today's talk. And Rob is one of the most versatile biophysicists I know, and he works both on protein folding and dynamics. And so he's a perfect fit for our webinar. And before he starts, let me tell you a little bit about Rob's career. He started out in Cape Town in South Africa, where he did his undergraduate degree in chemistry, and then went to Cambridge to do a PhD with Jane Clark. These were the early days of force spectroscopy. And Rob actually did experiments those days and pioneering work with AFM on protein folding and unfolding with Jane. But already at the time, he got interested in combining experiment and simulations, and he started collaborating with Martin Karplus, and also did a short but very productive postdoc with Michele Vendroscolo, where he started integrating experiment and simulations at a level that was actually quite uncommon at that time. So he was really pioneering concepts that we now cherish and use a lot. And then from Cambridge, he went across the Atlantic to the NIH to work with Bill Eaton and Gerhard Homer. And the goal was to directly combine experiments and simulations and theory. In this case, the experimental side was with a particular focus on single molecule FRET. And from the theory and simulation side, questions such as diffusive dynamics of protein folding, and also ideas about transition paths that emerged at that time. Then he went back to Cambridge as a Royal Society Fellow and lecturer in Cambridge and started his own group. And that went very well. And so after a few years, he actually went back to the NIH, where he is now a chief of the computational biophysics section. And this sort of ended the ping pong between Cambridge and Bethesda. And so Rob's key interest at the Laboratory of Chemical Physics, where he's now, are several-fold. On the one hand, he's developing novel simulation methods and theory. and broadly in the context of protein function and evolution. And more specifically, some of his key topics are protein folding, misfolding, aggregation, but also intrinsically disordered proteins and phase separation, which is something that he will probably focus on today. And in a lot of his work, really the close integration with experiment is a key aspect. And of course, he's ideally equipped to do this because he has hands-on experience with experiments and correspondingly a really deep understanding of experimental biophysics. And at the same time, he doesn't just apply established simulation tools, but he's really made important contributions also to force field development, and his developments are widely used. He's using simulations from coarse grain to atomistic, often inspired by direct integration or combination with experiments or cross-checking with experiments. And he's been enormously prolific, and he's been highly innovative in his approaches and his ability to really see through the even very complex results. And so his papers are full of insight, and the discussions with Rob are always highly illuminating. And so it's not a coincidence that, for instance, he recently received the Sackler Prize in Biophysics, which is probably the highest distinction in biophysics that we currently have. And so before Rob starts, just a few technical points to all of you. Please switch off your microphones. And if you have a question, just mention it in the chat. You don't need to explicitly phrase your question. Just say you have a question, we'll call you at the end, and then we can discuss. After a few minutes, we will lock the Zoom meeting because we've had some cases of Zoom bombing in the past, but the talk will be recorded and made available on our YouTube channel just in case you get locked out at some point in the future. And let me just mention our next talk 2 weeks from now will be by Brian Dyer on time-resolved spectroscopy on protein-mediated membrane fusion. So we hope to see you there. And if you are unsure about the times or dates, please have a look at our website, proteinfoldingdynamics.com. But now, Rob, great to have you here today. Thanks very much for joining us. And the screen is yours.
Okay. Thank you, Ben. Just a second. Sorry, just a second. I want to. Okay. Can you see my mouse? Because I can't. I don't know a pointer, but yeah. Thanks very much for the introduction, Ben, and thanks Gillard and Hagen as well for inviting me to present in this series. It's quite an honor to follow on from the people who've presented already. So I hope I can live up to expectations. And I'm certainly very much enjoyed hearing the other talks in the series so far. I'm going to talk a little bit about my work on intrinsically disordered proteins, essentially starting from one intrinsically disordered protein and kind of building up to complexes and then coacervates involving large numbers of molecules. So before I actually start, I wanted to throw in a couple of commercials. The first is for the Protein Folding Dynamics GRC, which I'm a vice chair of next year. Many of you will, of course, know about this. Hopefully, this will be an in-person meeting, so it will be really great to see all of you again. Preliminary program is up already. The second is a meeting that I'm co-organizing with Ben, Kristen, and Beda next year in Zurich, which has a title very similar to my talk, actually. And it's a meeting more focused on IDPs. Okay, so I guess the theme of my talk is how molecular simulations can be useful for studying IDPs. obviously IDPs populate a very heterogeneous ensemble of structures, and so it's challenging to obtain like specific detailed interactions from experiment. Simulations, of course, can readily provide that kind of information. Of course, they can also be predictive in terms of what would be the effect of changing the sequence. They can also be used in an integrative way together with experimental data. I'll show a little bit of that. And of course, they can be used to test theoretical models computationally. But also, IDPs are quite useful for simulations, as we found namely that they can reveal shortcomings of current energy functions or force fields. And they can also be useful for developing new force fields because of the sensitivity of the results to the parameters. So this is a rough outline of my talk. I'm going to start talking about properties of single IDP chains, and specifically protein collapse, and then go on to describing disordered complexes of proteins and proteins with nucleic acids, and then building up to describing coarse-grained models for liquid-liquid phase separation, and finally some initial steps towards animistic simulations of protein phase separation. So protein collapse, I'm going to start with some very kind of elementary stuff, but just kind of by way of introduction. I mean, homopolymers are well known to kind of collapse as a function of temperature. And so as you increase the temperature, the protein expands. So at low temperatures, you would find like a collapsed globule where the radius of gyration is approximately proportional to the third power of the number of residues. And at very high temperatures, you would find a self-avoiding walk. And at intermediate temperatures, you would have this so-called theta state where the attractive and repulsive interactions are exactly balanced, and the scaling exponent there would be equal to a half. And it's 0.6 under these excluded volumes with self-avoiding walk conditions. The reason I mention this is just kind of as background to the rest of the talk. Now, it's important to point out that actually proteins don't exhibit this behavior at all. Actually, initially, when you increase the temperature, they collapse and don't expand. But the reason for that is that the hydrophobic effect gets stronger with temperature. So initially, you'll see that the chains collapse and then expand. But this kind of idea holds for not just for changing temperature, but for changing the interactions between the within the protein, between proteins, for example, by changing ionic strength, adding co-solvents, or changing the sequence of the protein itself. And so, yeah, I mean, one can express this collapse in terms of the scaling exponent, nu, essentially going from a third to 3/5. I guess an obvious question is how collapsed are unfolded proteins, and the answer, or an initial answer, was provided by actually one of our organizers, Hagen Hoffman, who when he was working in Ventula's group, showed very nicely that unfolded proteins in water tend to be close to theta solvent conditions, whereas in denaturant, they're closer to self-avoiding walks. And that result was consistent with earlier SAXS experiments done in denaturant, where they found also a scaling exponent of 0.6 for proteins in denaturant. And there was some variation of nu in water, but essentially for most proteins, it was close to a half. So why do we care if proteins collapse? Well, there's kind of implications for a number of different areas. I mean, one, I guess, is protein folding. I mean, earlier work by Dave Thurumali, for example, showed that one doesn't want the protein to collapse too much before it folds, because otherwise it would slow down. So it would slow down folding. So for example, here he's looking at how much below the collapse temperature is the folding temperature, and he observes that that there's a massive slowdown of folding as that difference increases. So there's obviously an implication for protein folding. And in fact, I mean, for most proteins, I mean, well, for many two-state proteins, the collapse temperature and folding temperature are essentially the same. So the other reason that it's important is, of course, more recently, because of the observed relationship between protein phase separation and protein collapse. Namely, that if you look at phase separation, there's a critical temperature below which phase separation can occur, which is known for homopolymers to be the same as the collapse temperature for a single chain, T theta, and it turns out actually in practice that for simulations of a variety of sequences, this relation holds empirically also for heteropolymers as well. So I guess another reason is the very nice study recent study by Hagen showing that that there's a clear correlation of the dimensions of the unbalanced state of the IDP max and the binding affinity and rate. So I guess I've established that studying collapse of unfolded proteins or disordered proteins is actually something that's interesting to do. So then I guess the question is, how do you measure it? Here, unfortunately, there was historically a discrepancy between the two most common types of experiments to do this, namely small angle X-ray scattering, which showed essentially no change of radius of gyration as denaturant was increased, which is the easiest way of changing the compaction of the chain, whereas FRED experiments showed that the RG increases as the denaturant is increased. This discrepancy was seen in a variety of other studies. I guess the common feature being that SAXS tended to show no change of RG, and other experiments showed that there was a change of RG as denaturant was varied. So I guess there's several possible reasons. One of which is that it's harder to study the unfolded state in an ensemble experiment when its population may be very low. In other words, in SAXS, there could be some effect of FRET chromophores on collapse, or there's possibly selective partitioning of the denaturant into the unfolded chain, so that one can't assume that denaturant positions are correlated just with the positions of the unfolded protein. So our strategy, and this was a collaboration with Ben Schuler and Beata Krogelund. Sorry, this was a collaboration with Ben Schuler and Alex Grishev and Klaus Gast, the idea was to study two proteins where they could be studied over a wide range of denaturant concentrations, and both proteins can be studied at low denaturant without populating a folded state. So that makes it easier to do SAXS. And then we did kind of a conventional analysis of each kind of experiment, just to see what we would get. And lastly, we used molecular simulations integrated with experimental data to try and resolve the origin of the discrepancy between these experiments. So just quickly by way of introduction, SAXS gives you information on the dimensions of unfolded proteins from scattered X-rays, and the angle of scattering is, or the distribution of scattered intensity depends on the structure, as you can see by just looking at these SAXS curves for 3 different proteins. And it's dependent, in fact, on the distribution of pair distances within the protein. And there's a very nice simplification, a sort of model-free simplification, if you like, whereby one can, if one looks only at small scattering angles, then the scattered intensity, or the log of the scattered intensity, is proportional to Rg squared. So there are some requirements. So one must have sufficiently dilute solution, that there's no contribution from interparticle scattering, that there should be, one has to worry about background subtraction, but most importantly, the scattering angle Q has to be sufficiently small. So on the other hand, FRET measures a distance between a pair of chromophores via, in its simplest form, the Foster relation given here. And if you're looking at single molecule FRET, you can measure that efficiency directly from the ratio of detected acceptor photons. So you excite a donor chromophore, and then either it emits a photon, or if the donor and acceptor are close enough, they can be non-radiative transmission of excitation to the acceptor, and that would then emit a photon. And so you can get this efficiency from the ratio of acceptor photons to the total. So these are the basic results that came out of the study on the unfolded, on R17, which is a destabilized version of a folded protein, and actor, which is an intrinsically disordered protein. So you see, this is studied as a function of 2 denaturants, but essentially you see that there's a reduction of transfer efficiency with increasing denaturant concentration, as we sort of expected. So that means that the chain should be expanding. So how do you quantify that expansion? So one only measures a single number, namely the efficiency. So usually one has to integrate it over some form of the di-di distance distribution. And I'm showing here 2 different examples of such a distance distribution for a Gaussian chain or self-avoiding walk, which are just 2 different polymer models. And you can see that obviously these distributions are different. And indeed, the results that you get for the inferred distance are somewhat dependent on what polymer model you use. So that's the story with FRET, that there's a model dependence to the inferred distance and radius of gyration. For SAXS, these were experiments that were done by Alex Grishev. What you see is that actually, if you look at the Gunia plots of the log of the intensity versus Q squared, you see that there's clearly actually a trend of changing slope with denaturant concentration, and that one can see by plotting the Rg versus denaturant concentration. But what's interesting is that the results depend quite a lot on the range of Q that you fit to get this Rg. And if you choose a smaller range, then you get a larger effective change of radius of gyration. That suggests that, fitting too large a range, which is often, which was, often previously done based on folded, what was safe for folded proteins, at the maximum fitting range of Q times Rg is less than 1.3. If you apply that to IDPs, you suppress the changes of Rg that occur with denaturing concentration. Using a smaller range, you can clearly see a larger expansion. The problem, of course, is then you start getting into noisy data, and so the errors get much larger. So we tried to, although the FRET and SAXS are at least qualitatively pointing in the same direction here, we wanted to get an overall consistent picture of what was going on, and so we resorted to ensemble fitting, which is where we use a molecular ensemble generated by simulation, and we reweight it to match both sets of data. So in this case, we used the absinthe implicit solvent model from Rohit Papu's group, which just a quick way of generating a good initial ensemble. And then we chose weights to maximize the agreement with the experiment. Obviously, if you have many structures in your ensemble, typically like 10,000 or more, this would make you susceptible to overfitting. So one adds a regularization term here, where you essentially try and keep the weights as uniform as possible. So in other words, you reweight the simulation as little as possible while still fitting the data. So if we did that, we found that we could fit both the SAXS data shown at the top here and the FRET data with 3 different labeling positions very well. And so I guess the bottom line is that the 2 experiments are completely self-consistent, and the ensemble fits are similarly suggesting an expansion. I guess one can get a little bit of extra insight just by looking at the dependence of by using simulation data where there's basically no noise in order to do the Guinier fits. And then what you can see is that you really have to get to, I mean, if this is the true radius of gyration, one really has to go to a pretty small fitting range in order to match the true radius of gyration, and using a range of a Qmax of 1.3 is clearly too large. So I guess the bottom line here, just summarized in this figure, where we're looking at the both the end-to-end distance and the radius of gyration in red coming from our ensemble fitting. What you can see is actually that the end-to-end distance tends to fit to a Gaussian chain. It tends to match the results from fitting a Gaussian chain to the FRET data quite well at low denaturing, but then approaches more of a self-avoiding walk, or the results from a self-avoiding walk at high denaturing concentration, which is, I mean, not entirely unexpected, as we sort of discussed earlier. Proteins do tend to switch from close to a theta solvent or close to Gaussian chain conditions at low denaturant to close to self-avoiding walk at high denaturant. Yeah, and then I guess want to just mention that if one uses a small enough range of Q, one can actually get results that are consistent with the ensemble fitting using a traditional Guinier fit to the SAXS, but of course then the error bars can get very large. I just wanted to point out that a couple of other groups have obtained consistent results. For example, Ed Lemke and Rohit Papu and Dmitry Svergan also looked at FRET and SAXS for unfolded proteins and found similar results. And more recently, Tobin Sosnick showed that there was a change in radius of gyration as the denaturing concentration was varied. I guess I just wanted to highlight a few methods as far as, so I guess I mentioned how, conventional methods of interpreting FRET or SAXS had some shortcomings. So I guess out of this, kind of potential improvements did come. Firstly, there was this for FRET, former postdoc of mine, Wenwei Zheng, developed a neat way of interpolating between different solvent quality in fitting FRET data to proteins. And then for SAXS, we also developed a kind of extended Guinier analysis, and Josh Ryback and Tobin Sosnick developed a so-called molecular form factor method. And all of these methods extract coupled estimates of the radius of gyration and the scaling exponent from the experimental data. So I guess that sort of summarizes how one can study single protein chains using FRET, SAXS, and simulations. So I wanted to switch gears to talking about disordered protein complexes and disordered complexes with nucleic acids. So I guess the first example is was also prompted by collaboration with Ben Schiller's group and with Beate Krageland's group in Copenhagen, where they were looking at the association of the histone H1, which you may recall is the one that sits here at the this kind of diad position in the nucleosome and kind of holds the linker DNA together, and so they were looking at the association of this highly positively charged protein with Prothymosin alpha, which is believed to be a chaperone for H1. Oh yeah, I just wanted to point out that, although H1 has the small globular domain, which is what's actually resolved in the structure here, most of it is disordered. And in fact, as I'll show, that appears to be the more important part. First of all, I just wanted to point out that, so they used, Ben's group used a single molecule FRET to measure the binding affinity by having a labeled Prothymosin alpha and adding H1, and doing this as a function of H1 concentration. You can extract a dissociation constant, which is of the order of picomolar at physiological salt. So that's really remarkable for the association of two disordered proteins. The other thing I wanted to point out was that if you do away with the globular domain and just use the C-terminal tail of the H1, then you get almost exactly the same affinity. So what was surprising, though, was despite this high affinity, this complex was really extremely dynamic. Sorry, I don't know what happened to this picture, but the correlation functions from nanosecond FCS showed roughly the same decay rate, both in the complex and out of the complex. So this appears to be a highly dynamic association, they measured Fred efficiencies for a matrix of donor and acceptor chromophores on the Prothymosin and on the H1. So I guess the question though is, how do you turn what are obviously ensemble averaged efficiencies in a dynamic complex into a structure, and that's where we came in with simulations. So in this case, I chose to use the kind of simplest possible bead model for the protein. We started actually with something more complicated, but then we kind of stripped it down to the bare essentials, which is that you just have some bonded terms keeping the chain together, and some Go-like terms keeping the globular domain of the H1 folded, and a simple Debye-Huckel screened electrostatics, and then a uniform, for everything else was just a uniform protein-protein interaction where we tuned only this protein-protein interaction parameter in order to match the experimental data. So it turned out actually just tuning that one parameter, we can really match the Fred efficiencies, experimental Fred efficiencies remarkably well. These two curves are just simulations without kind of chromophores attached or with simple coarse grain chromophores. And these nicely bracket the experimental Fred efficiencies. So it seems that this model, which really the only difference between the residues is the charges on them, captures very well the structure of the complex. So it indicates that the electrostatics are what drive the association, and we also looked at the affinity for binding a second molecule of H1 and Prothymosin, and that was turned out to be much higher. So that kind of indicated why this could be found as like a one-to-one complex at single molecule conditions. And there's some qualitative validation of this result in the fact that the regions of the sequence where the NMR intensities are suppressed turn out to be correlated with the regions that are where the Prothymosin is forming the most contacts in the simulation with the H1. So just looking at what does the structure look like? Well, it's a little bit hard to really describe it. We kind of projected it onto a number of principal components, and what you can see is, well, I think if you look at the contact map, it's maybe a little bit clearer that basically the main region of Prothymosin alpha, which binds, tends to be the C-terminal region, which is most charged. Whereas pretty much the full length of H1, which is more uniformly charged than Prothymosin alpha, is involved in binding. Last thing I wanted to mention is just that we recently, through some very elegant work by Andrea Sottini, helped to resolve the kinetics of exchange of Prothymosin with H1, where the involvement of a ternary complex was found to be critical. I'm not going to talk about that, but I think it's a very interesting result which you may be interested in looking at. So I guess the next thing I wanted to talk about, I guess, moving on from like protein-protein disordered interactions, was protein-nucleic acid disordered interactions. And here again, this was a collaboration with Ben, where we were looking at the binding of a piece of nucleocapsid domain of the hepatitis C virus core protein which is believed to be an RNA chaperone. In this case, we looked at chaperoning of a model DNA hairpin. I guess the question is, how exactly does the chaperone accelerate the folding? And to answer this, we used a similar model to the one that was used for the Prothymosin, but for the protein, but for the nucleic acid, we just used 3-beat residue. And in this case, we just we optimized the stacking energy to roughly capture the efficiency of isolated single-stranded DNA, which is essentially capturing the persistence length of the single-stranded DNA. And the same electrostatic model as before, and a simple Go model for the DNA duplex. And then the only adjustable parameter to the complex data was to adjust the protein DNA interaction in order to match the FRET data. Again, we were able to match pretty well the FRET between the DNA and the NCD. There's a large number of labeling pairs, and they were all matched pretty well, as you can see in this correlation. So, what can we say about the actual chaperone activity? So the experiments that Eric Holmstrom did were based on immobilized DNA, and then a free diffusion chaperone, which would come along and bind, and then dissociate. And what happened when by analyzing those separate regions of the trajectories, you can get an estimate for how much the chaperone binding increases the rate of folding, and that's similarly seen in simulations. If you have the chaperone and the DNA freely diffusing in your simulation, you get the chaperone binding, which increases the folding rate of the DNA and stabilizes the bound state. Stabilizes the folded state. The essential feature of the mechanism is that the chaperone is able to stabilize the collapse state of the DNA. If you look at the acceleration that you get or rather, if you look at the compaction that you get by binding to the chaperone, if you had to mimic that by adding like monovalent salt, you'd be adding essentially molar quantities of salt, which is clearly not a biologically plausible mechanism. And similarly, one would have to do the same thing to match the acceleration and folding rate that you get with the chaperone. Essentially, it seems like the protein is acting as a large macromolecular counterion, and we were able to demonstrate that this is really the major effect by first simulating the potential of mean force for the radius of gyration in the presence and absence of the chaperone, and then we just worked out what you would need to add to the chaperone-free DNA in order to match the RG with the chaperone. So we just added an external potential to match them. And so we can exactly match the collapsing effect without having any other kind of interactions, changing any other interactions. And what we saw is actually that the rates, I guess the folding rate is accelerated by a certain amount, and when you have when you just use this external potential, you accelerate the folding rate by the same amount, but there's it actually gets accelerated even more. That's just because there's a kind of a lack of internal friction. You see the unfolding rate is also accelerated, but you can scale both of these down according to account for this internal friction effect, and the scaled rates match extremely well with the rates that you get from the simulations with the protein bound. So this really suggests that the effect on the kinetics comes entirely from the effect that it has on the collapse of the DNA. I just wanted to talk quickly about how we've recently been extending this model for protein DNA interactions to look at to look at coacervation effects, and this is work done by a postdoc in my group, Kate Liebold. So she looked at I took this diagram of different kinds of phase separation driven by interactions between different components in a two-component system from this review that Greg Dignon wrote last year. And you can and so there's various possible forms that you can get for this phase diagram depending on the strength of the relative strength and interactions between the components. Obviously, for a highly positively charged protein interacting with DNA, one would expect to see this kind of a cross-interaction driven assembly, which leads us to expect a phase diagram of this form. So the individual components are self-repulsive, but attract each other. So Kate chose to look at a system which was studied by Catherine Stott's group in Cambridge, where they used the C-terminus of H1. So I've already introduced that. It was shown to be primarily responsible for binding of the Prothymosin, and they studied this in combination with DNA oligomers of different lengths, and they were able to see that that these phase separate under when they're mixed in roughly equimolar mixtures, depending on the DNA length, obviously. And that also in this complex, the CH1 appears to remain unstructured. So we're looking at a highly disordered complex. And they found that the optimal DNA length was about 20 base pairs, which roughly matches the charge on the CH1. So that kind of makes sense. Kate used essentially this very similar model to what was used before for this NCD DNA interaction, but we separately optimized the protein DNA interaction against the measured KD for binding of this 20 base pair DNA to the CH1 under physiological salt. And it turned out that we only needed to change the protein DNA interaction by a really tiny amount, which was kind of impressive considering that we're looking at different protein sequences here. And the only difference the only thing that we can vary in our model to represent the sequence is this non-specific parameter epsilon. So we used this slab simulation method to study the phase coexistence, where you essentially have an elongated simulation box where you have a high density region in equilibrium with a low density region, and that allows you to just by running long simulations determine what the concentrations are of these under different conditions, and I guess, as you might expect, we got this sort of form of the phase diagram characteristic of coacervation between oppositely charged components. As you might also expect, increasing the salt concentration destabilizes this kind of interaction. At some point, it becomes unfavorable to phase separate. What was interesting, though, was that as you increase the salt concentration, or rather, as you decrease the salt concentration, you get an increase of ordering of the dense phase. And to characterize this order, we used essentially kind of like a local pneumatic order parameter, where instead of calculating this over the whole system, we just evaluated it, essentially the alignment of different DNAs, which were within a 4.5 nanometer radius. So it's telling you that that those do tend to become more aligned as you go to lower salt concentration. We next looked at how sequence variations in the CH1 might affect this this result. And so at the top, I'm showing here the wild type CH1, which, as I mentioned before, is close to sort of uniformly, or a uniform distribution of charges. And then we did some synthetic variations where we just distributed the positive charges in blocks of varying sizes, ending with this most extreme example where all of them are at one end. What you see is that one can characterize this, by the way, sorry, in terms of this sequence charge decoration parameter proposed by Kengshuk Ghosh, which I'm plotting on the right here, and you can see that as you go to more consecutive protein residues, you get to a lower value, right? Yeah. Of the SCD. I guess the the important point I wanted to make here is that initially what you see is as you start clustering charges together, you increase the propensity to phase separate, and that's kind of logical because you increase essentially the cooperativity of the binding to the for the protein to the DNA. You've got, each time you have a positive charge that binds to the DNA, then all the ones that are next to it can also bind, and so that reduces the entropic penalty for binding. So as you see initially, there's an increased propensity to phase separate, but then what's interesting is as you go to even more extreme clustering of charges, then the ordering of this of the dense phase really starts to steeply increase, and so that raises the question: what is causing that ordering? So one can look a little bit at the I guess. So this is with the kind of most mixed charge sequence, and you can see everything is kind of looks to the eye more or less random, whereas at these with the most segregated charges, you're really seeing now a kind of separate domains of protein and DNA forming, where the DNA strands do tend to be kind of aligned with each other, so this this suggests that you can if you go to the extremes, you can get kind of an interesting ordering of the DNA taking place. And so we asked the question whether, I mean, whether these such extreme sequences could really exist in reality. And looking through the DisProt database, which is of course not complete, but at least gives a large number of disordered proteins, we did find that proteamines, which are responsible for packaging of DNA in sperm, which is very dense, compact state, do tend to have a similar kind of clustering of charges to what we have in this synthetic situation. So it will obviously be interesting to explore that further. Just wanted to kind of, so I guess, so switching gears, I've spoken so far about using a kind of a very simplified model of the protein where there's no sequence dependence. And obviously there's a limit to how far you can push that. It works well in this kind of examples I've spoken about where charges are kind of maybe a dominant effect. More generally, one would want to have a sequence-dependent protein model, and in collaboration with Chaperone Metal, we developed this so-called HPS model, in which one has like similar bonded terms and electrostatic terms to the previous model, but in addition, you have a sequence-dependent contact potential. And we optimized that to match the radius of gyration for single protein molecules, inspired by the observation that this should be related to that the collapse temperature should be related to the critical temperature, phase separation. And we found that, you know, having done this, we could qualitatively reproduce this map of charge versus hydrophobicity that was proposed by Iversky, as well as this kind of Papu style plot of sequence space. And just to kind of give some sort of idea of the qualitative things one could look at with this, I mean, you can look at the effect of changing charges by phosphorylation, where so as you increase the number of glutamates mimicking phosphate, you find there's a depression of the critical temperature, and that's kind of mirrored in these experiments by Nick Fauzi. And similarly, we found there's longer chains are more inclined to phase separate, which is also consistent with experiments. So I guess recently several groups have been involved in trying to improve the accuracy of the HPS model. One thing that Jatain's group has done is to look at incorporating temperature-dependent effects, which is clearly important for some kinds of experiments. And they've also looked at we've kind of independently looked at making this model more accurate. So in this figure, I'm showing some of the flaws of the original HPS parameterization, which was that it gets. I'm showing here the plot of RG versus the number of residues for a bunch of proteins. The solid symbols are phase separating proteins, and empty ones are not phase separating proteins. So it shows you that it's getting the radius of gyration in the right ballpark around this nu of a half, which would be the boundary between phase separating and non-phase separating, but it's not terribly predictive of which is which. And as far as the properties of single chains go, it tends to predict that they're too collapsed. So we thought, oh well, we'll go about trying to optimize that. So what if we just kind of scale globally effectively scale globally all of the hydrophobicities. And we found actually just by doing that, we could match the radius of gyration of these single chains very well, but then we were not able to match the phase separation. And if we change to a different hydrophobicity scale, the Kite-Doolittle scale, we got we found that again, we were able to reproduce the radius of gyration of individual chains, but for these phase separating proteins, we found that essentially none of them were predicted to phase separate. So I guess we could have kept trying different hydrophobicity scales until we were blue in the face. But I mean, anybody who's looked in the literature knows that there are like hundreds of them. So we decided instead to optimize the hydrophobicity scale against experimental data. So we used as the method this force balance method, which has been described by Liping Wang and used to optimize water models, for example, against experimental data. Essentially, are just trying to minimize the deviation between some experimental observables and your calculated ones by changing the parameters. And you do a gradient descent to find the optimal parameters. And I just, Preston Lindorf-Larsen recently reminded me that actually they had proposed doing something similar in this paper from 2008. So first of all, we tried training the model just using only proteins which didn't phase separate. And then what I'm showing here is what the trained model predicts for the radius of gyration for non-phase separating proteins, and then the radius of gyration for a set of non-phase separating and phase separating proteins. And you can see that it doesn't. You can get these radius of gyrations for the single chains pretty well, but you don't predict phase separation all that well. Now, on the other hand, if we train only on a database of phase separating proteins, then it kind of goes in the other direction. In this case, we kind of used a trick because we don't know in most of these cases what the radius of gyration is, but we know if we assume that that these should generally have a nu of less than a half, we can calculate what the radius of gyration, their radius of gyration would be if they did have nu equals a half, and then restrain it to be so essentially target values less than that in our optimization, which is what this contribution from the phase separating proteins to the target function does. And it turns out if we do this optimization, we're able to both improve the cross-validated RG for non-phase separating proteins, and also to better discriminate between phase separating and non-phase separating proteins. What was kind of interesting, I guess, was that we do get sort of significant changes. I guess notably glycine turns out to be kind of relatively hydrophobic. Of course, there's always the usual suspects like these kind of aromatic residues like Phe and tyrosine, which are well known to be involved in phase separation. And if you kind of just compare it with a bunch of different hydrophobicity scales, you see that it doesn't really kind of match too well with any of them. It's probably closest to the Wimley-White scale for membrane protein hydrophobicity. I guess just last wanted to show what the what the effect of using a different hydrophobicity scale would be on this kind of on this Tversky sort of plot of mean net charge versus hydrophobicity, which with the original Kite-Doolittle parameters that it was initially developed with, you see that these are the top 8,000. So it's just a set of folded proteins. The gray is a set of phase separating proteins, and then blue is the whole of the disprot disordered protein database. And then it looks in this case as though the phase separating proteins are the least hydrophobic of all, whereas in our optimized potential, these actually turn out to be the most hydrophobic. And that kind of explains why just, switching to the Kite-Doolittle force field didn't help us in terms of predicting phase separation, when actually needed to change, systematically change the hydrophobicity scale in order to get the kind of correct trends. So I don't know how much time do I have, actually. I might be a little on the long side here.
Yeah, we're already at an hour or so, but
yeah, okay. So let's just skip this last section, I think. So I'll see if I can, how quickly I can zoom through that. Okay, so yeah, thanks for bearing with me for that long. So I'd like to thank the people who did the work. So I guess first of all, thank my group members, Kate and Thomas, who respectively worked on the protein nucleic acid interactions and the and optimizing this hydrophobicity model. And I'd like to, of course, thank One-Way, my former postdoc, who did all the stuff on this comparison of SAXS and FRET, and all my collaborators. Okay. Thank you.
Thank you very much, Rob, for this wonderful tour from protein collapse to phase separation and interactions of all kind. There are already quite a few questions in the chat. So the chat was in general quite lively today, so I hope I'm not missing anything. But the first comment came from Sophie Jackson. Sophie, do you want to?
It was a very small comment. I guess the other reason why you would not want an unfolded chain not to overly collapse is you increase the chance of knotting if it's highly collapsed. So it was just yeah, you could include it. It doesn't really matter. I'm sorry, it started quite a lot of chat going.
That's good. That's good.
Oh, sorry, I've missed all of that. I'll have to catch up on
yeah,
it.
no,
Robert, don't worry about it.
Okay, then next question that also triggered quite a bit of discussion in the chat was from Stephen Fried about IDP expansion. Stephen, do you want to still pose your question here? I'm not sure he's still around. Maybe he had to leave already.
It sounds like the chat was.
Yeah, no, I just check. I don't think Stephen is here anymore. So he
Stephen is not here anymore.
Yeah, that's what I just realized. He was wondering why IDPs would still expand in a denaturant-dependent manner, similar to what folded proteins do. I don't know if you want to briefly comment.
Yeah, I mean, I guess because I guess the answer is because they can most of them are not close to this excluded volume limit, apart from things like Prothymosin and I mean, so most of them are closer to a kind of theta solvent chains, and as a result, they have room to expand and they can bind denaturant just like regular folding proteins. So then they'll expand.
Yeah. And Eric Martin had a comment on this. Do you want to also comment here, Eric? I'm not sure. Maybe he also had to leave. Yeah. So his comment was
anymore.
Yeah, but you can read up on his comment in the chat. Then Bill had a question regarding time-resolved SAXS. Bill.
So, Robert, I guess it's 14 years ago that we were comparing our own measurements on protein L and Gilad's measurements with the experiments on SAXS. And there is this stop flow experiment by Plaxco, Doniak, and Baker, which showed that in going from 4 molar to 1.4 molar guanidinium, not only did the protein not collapse, but it even expanded a little. And I don't recall asking you about this, even though I followed your work with Ben quite closely. I don't recall asking you for at least a couple of years. Have you guys converged on an explanation of why the stop flow experiment showed no collapse? Ben? Robert?
I think it's just a question of sensitivity. I mean, they're really working at the absolute limit with that. And of course, there's possibility of, they have to also work at higher protein concentration, I think, to do those experiments that might have something to do with it. Ben, do you have some comments?
Yeah, I mean, I think it is a really challenging experiment. I agree. Yeah. So,
yeah, nobody's tried to.
They did report error bars, and it wasn't a matter of them using too large a range in the Guinea plots. So that's why it's still puzzling. I mean, the only thing that we suggested at that time was that the protein-protein interactions contribute to the RG, and that might expand the observed RG from the high concentration. But then I think there was a subsequent calculation that Seb sent me, a private calculation that said, no, that couldn't, it was not concentrated enough to have an effect. So I think it's still a real puzzle.
Not every experiment is done right.
Depends what laboratory you're in, Peter.
That's correct.
They're never wrong in my lab or Ben's lab. Ever.
That's a very optimistic view, yes. Okay, but Peter also had a question about second shell Walter-mediated interactions.
Yeah, I just wanted to, I'm a little bit, I may have missed actually a slide, but the model that you're using to kind of fit the simultaneous phase diagram of the monomers and the phase separation, I don't recall it having a second water-mediated potential well. And that sort of surprises me that you can kind of get everything to work, because we know that the cold denaturation comes exactly from the second water-mediated shell and clathrate formation. That's why we know that the phase diagram under temperature and pressure has to take into account that well. And we know lots of systems where interactions mediated by a single water are crucial to even getting binding of particular proteins. So it's kind of, well, I don't know. Did I miss that you have a second well in there and it just wasn't there in the, and I'm just not thinking right?
No, there was no second well. Yeah, so I guess I mean, I guess if you have a more complicated pair potential, or you could, in principle, capture richer effects, but at the same time with the, you're not really looking. I mean, that solvent separated minimum, you can end up overcounting your solvent contributions if you have a dense.
It's just that we already know it explains the cold denaturation quite quantitatively, so that's why and also qualitatively. I mean, when there's an effect that you qualitatively know is there and is significant in several cases, like you can't get crystal structures right without that interaction for many complexes. So it just seems like it should be the default model to perturb from, rather than trying to force fit it to a single contact interaction. But, oh well.
Yeah, I mean, potentially we could do better with the solvent separated minimum, I guess. But are you able to get the cold unfolding without changing the potential as a function of temperature? I mean,
no, obviously you have to change the potential with temperature. They're always.
So we could also get cold unfolding.
No, I know you can, but that doesn't mean that it's right. I mean, that's the point. I mean, you have to show that your model does other things.
Okay.
And you're sort of developing a rather simplified model that only does sort of, I would call it sort of statistical mechanical properties right, which is nice. And it's nice to understand to people that you know, basically it's just the B2 coefficient of your potential that's important. But you know, you can't literally believe that your potential is correct to 0.05 kilojoules per mole per residue, right? That would be kind of strange. I mean, to believe that that's literally the actual potential independent of temperature, that would be, that pushes me to the edge anyway. Okay.
Don't go over.
Yeah.
Okay. Then we have another question from Jarell Joseph.
Hi, thank you, Robert Best, for this very good talk. My question was with regards to the coarse-grained model that you optimize using the force method. In your optimized parameters, in the slide, you show that glycine is basically more hydrophobic than the aromatic residues, or comparable in hydrophobicity to the aromatic residues. That means that, like, within the framework of Rohit Papu that speaks about stickers and spacers, then glycine basically is behaving as a sticker and not a spacer that it is commonly classified as. And also experiments find that when you replace aromatic residues with glycine, liquid-liquid phase separation gets suppressed. So how is this optimized parameter justified?
Well, that's what it. Yeah, that's what we came up with. I haven't. Yeah. Yeah. I mean, it's a little bit counterintuitive, but I mean, I guess that. I mean, also from Rohit Papu, I guess there's some evidence that polyglycine is collapsed in water, which would suggest that it's hydrophobic. Yeah, I mean, I guess we have to look at the what you're talking about, which is the effect of substituting residues with glycine. Yeah.
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 Okay.
I mean,
Then,
of course, the residues are not the same size, so that does have an effect as well. But yeah, I take your point that is a potential issue.
Then Hagen had a question.
Yeah. Thanks a lot, Robert. It was really a wonderful summary of an enormous work over the past years. My question was also about the coarse-grained model and your attempts to discriminate or to identify sequences that can phase separate using the coarse-grained model. I was also a little bit confused about the high hydrophobicity of glycine, even though in the end, if you think about it, it's not so surprising because your model basically has one interaction parameter And it's clear in order to get phase separation, you need to have strong interchain interactions. So you need to increase the strength of interactions of those amino acids that are prevalent in those sequences, which apparently seem to be predominantly glycines. I was just thinking maybe maybe there is another way of sort of supplementing these models using by introducing something like H bonds, which are currently totally missing in the in those coarse-grained models. Sort of orientational depending interactions. Would this already? I mean, it would of course make the model more complicated. It would introduce another an additional parameter, but maybe that's an alternative way to go to sort of make the model slightly more sophisticated, but not so sophisticated that you can't fit them to experiments anymore. Do you think there is sort of this way would be possible?
Yeah, I mean, yeah, I would probably go to a higher resolution model before including those kind of H bonds. And I mean, this is a really simple 1 bead per residue, but if one went to having a kind of a side chain bead and a backbone, several backbone beads, then it would make sense indeed to add specific orientational hydrogen bonds. I mean, there are of course models out there that do that. Yeah, I think that's possible. I mean, that would be a more sophisticated model than this one. Yeah.
And do you think it would be worth doing this step, or would it rather than make sense to go to the all-atom model directly?
No, it probably would be worth doing because there's still a huge saving in computation, even if you add a few more beads per residue. I mean, yeah.
Okay, next question was from Raphael Petrosian.
Yeah, thanks for interesting talk. So in case you have more than one interacting IDPs, as you had Prothymosin alpha and Histone H1 complex, how do their interactions affect the individuals' chains, end-to-end distance, and radius of gyration? Have you looked at that?
Sorry, I missed the first part of the question. If you've got more...
So if you have more than one interacting IDPs, right? How these interactions would affect their end-to-end distance and radius of gyration, individual ones?
Oh yeah, I mean, you'd expect that if the interactions are attractive, that you would get expansion of the chain. So IDPs which might be collapsed on their own would be expanded if they were interacting with other IDPs.
So in case of this Histone H1 and Prothymosin alpha, they should expand because there was strong affinity.
Well, those, yeah. So those in that case, yeah, they would collapse in that case because the proteins, the interactions of each protein with itself are repulsive. So yeah, once you add the other, once you add its partner, then it's going to tend to collapse.
Okay, thanks.
And Jose had a question.
Okay, sorry. First of all, Robert, it's a very, very nice talk. And you know that I love coarse-grained models, and I like to figure out which the most appropriate model that we are doing here. The question I have to ask is basically a little bit on the spirit of Peter, basically how much can you coarse grain? We have to I also love the water separate potential, but say how can we leave enough without it? And people are asking lots of questions about resolution of the model. Can we go to all atoms models and stuff like that? The data that you're using here, that's an interesting question. It's a very low resolution data. There's a lot of flopness, boson, SAXS, and FRET experiments, right? So in a certain way, it's a very interesting question that I have on, that we have been interested in before any other models. How can you get sort of a low resolution data, but it's still because you have a physical model behind it, try to get a higher resolution model, even so the data is a little bit lower resolution. Do you want to comment on that?
Yeah, I mean, yeah, so in that case, I guess I mean, if you're wanting to get higher resolution than the data are really able to give you, you're relying more on the accuracy of your model, I guess. That's yeah. I mean,
But I think that goes back to what maybe Peter was asked. You can fit some data, but the question, you have to sort of predict other data. How we do some self-consistency here? I think that basically I can go back to the question, do I need to include the water separate model or not? Or like Ben was raised, can we do a water model? How do we actually verify if we get the model is something I can believe?
Well, I mean, I guess I mean, the verification we did was by predicting results for chains that weren't included in the fitting, but yeah, I mean, and I mean, I guess similarly for, I mean, atomistic models, I mean, we've, fitted those to, FRET data and then used them to, I mean, other people even have used them to predict, SAXS data, but I'm not sure what you're getting.
You have all these different family of models, right? So basically, I love the coarse grain model. The question is, does it make sense to go to lower resolution? Can I trust it? Basically, if I do to a certain level of resolution that's consistent with the data we can believe, the question is how much you can fit this data to try to sort of set the parameters of your model, and how much resolution can you get depending on the quality of data that you have, or the resolution of the data you have. So I think that's always a crisis you have with these coarse grain models, right? So I just trying to figure out, since you're doing all these different class of model, you probably can compare them.
Yeah, I mean, I guess, yeah, I mean, that's true. I mean, of course, yeah, I mean, I guess, I mean, I don't know, for example, for the Prothymosin H1 interaction, for example, I mean, I guess, we really used like an absolutely minimal model, and I mean, I guess that exposes what are the key interactions that are present there. I mean, one can.
I mean, one thing that I found very reassuring is that you can use this model with virtually no modifications and apply it to a completely different system, and it still does a pretty good job.
Right, but the nice thing now, Ben, is that we can start to quantify pretty good, right? And that's the beauty of it. It's just not qualitative what we get. So I think now that we have this family of models, you can tell me what pretty good equals to what, or give an equation for pretty good. And I think that's what I think. I think with this amazing work that Robert has done, now we sort of have this family of models and all this data, we can sort of go one step beyond of what we have been doing.
Yeah, I mean, well, I guess very good just means, being able to predict, some other data. I mean, for a different system. I mean, that, I don't know how much better you, I mean, anything else is just, if you're predicting, I mean, you can only compare with things that have been measured, but, I mean, I was thought initially you were asking about, filling in details that one couldn't, they weren't really in the experimental data.
I agree with you, but that's the other part of it. That all comes together, right? Basically, that all comes together. I think one thing is basic, get the model, how much can I believe, basically? I don't know, what's the precision? Do I trust the energies on what? 0.1 kilocalories per mole? What's the level we believe? If we predict spatial, what we can do. The other thing I think is, but they come in parallel. They appear to be different questions, but they come in parallel. That's basically, because you have a physical model you start with, right? You're not doing just machine learning with no knowledge whatsoever. You're doing some learning together with initial model. Then even so your data is on lower resolution, you can still get a higher resolution because you believe on the physical model. And I think that's another interesting question that I think with the models you have, we can start to address now. So I think there are two things in parallel. They're great things. So they're all open-ended questions, but I think you can actually start put numbers on all of them. How much can we believe in both of them?
Mm-hmm. Yeah, no, I mean, certainly, you know, interrogating the model further, I mean, you know, by making other measurements is, yeah, going to be useful to see how much we can believe it. Yeah.
Anyway, it was very nice. It's interesting. There's a lot of food for thought here on how to put all this together into.
Yeah, we are approaching 6:30 here, or X30 somewhere in the world. I don't see any other questions in the chat. If I've missed anyone, please just speak up now. Or be silent forever, or whatever you say in English. Okay, so there are no other questions. So then thank you very much again, Rob, for a fantastic talk. Thanks everyone for joining and for discussing, and we hope to see you in 2 weeks for our next webinar. Have a good
Bye-bye.
day, afternoon, night. Goodbye.
Bye all.